Today we are here to listen to Etienne Caron. He's an active member of the North American demo scene in the 19s. Etienne was the main organizer for night demo parties in 95 and 96. Now he's on the Android team, leading developer at passwordbox.com. Etienne is also the current lead of the GDG in Montreal, Android. So GDGs are the independent Google-backed developer groups. And as an active member of the Montreal mobile developer community over the last 5 years, he's had the chance to organize and take part in multiple local hackathons and events. He's also had the pleasure to do talks on various Android game development APIs and platforms like Unity, libGDX, Cocos2D, OpenGL, Android NDK usage, and so on. So he's very happy to give a presentation today. He's happy that you're here. And I'm really curious what we will hear from you. So,
thank you. So I'll be a little bit redundant. I will thank you all for being here because that other keynote also seemed very interesting. So I will try to make it worth your while. As mentioned, I used to organize demo parties in the 90s. Some of you have actually been to those demo parties. I was quite happy to see you all last night again, and can't wait to catch up. I also, as mentioned, I worked for a company called Passwordbox. I put a few photos there so you could, put faces a little bit or get a feeling for what these companies are like, what that company is like, and what that group is like. Now, thing I want to mention at this point is I often say to friends that I don't like nostalgia. I'm not a big nostalgia fan. And I just wanted to warn everybody here that this presentation will make a total liar out of me. So, quick questions. In this room, if you could raise your hand, like developers of all stature, languages, and whatsoever, like who here is consider themselves a developer? So yeah, I would figure. Android developers in the room, specifically Android. I see a few hands. So that's good, because we're going to be talking about Android today, and the least hands that raise, I'm happy, because I will be teaching people something. I also would like to know specialized graphics developers, just to get a feel for, yeah, quite a few of those, obviously. So, good, good. Today's talk is about procedurally generated content. And I will start off my presentation by showing a few historical applications of procedurally generated content. Now, the reason this is interesting is because nowadays, on mobile, we see this interesting flashback to the old days where, comparatively to what's available on desktop, we have a very limited resource environment. So I think it's kind of practical to, or useful to look back and see how people dealt with these kind of limitations back when we were on 8-bit computers. So the first item of business in the historical flashback is Conway's Game of Life. You're probably familiar somewhat with it, but I just want to give a little flashback and remind you all what it's about. So it was created in 1970 by a mathematician called John Conway. And no, sorry, I'm mixing everything up. Conway was actually inspired by mathematician John von Neumann, sorry for that, who attempted to find a hypothetical machine that could build copies of itself. Now, von Neumann came up with a working model that was extremely complex, and Conway actually came up with a very, very simple set of rules that could fit the challenges put forward by von Neumann. So for those of you who may not remember like the basic rules, any cell on a grid, so the Conway Game of Life is basically a grid of on or off binary items. Any cell that has fewer than 2 live neighbors would die, as if caused by underpopulation. Any cell with 2 or 3 live neighbors will live on to the next generation. Any cell with more than 3 live neighbor would also die, as if overcrowding, as if by overcrowding. And any dead cell with exactly 3 live neighbor becomes a living cell again, as if by reproduction. So those are very simple rules. And the game itself is played by setting up an initial grid and looking at the results that come forward. So this game is interesting because you often see emergent behavior. So I have a bit of a taxonomy here on the screen of the few types of things you can see in the grid. The first row, you have blocks and loafs. These are stable configurations that would never change from one iteration to the next. Underneath that, you have beacons that are not flashing for some reason, but typically, typically beacons, you'd see them blink, so they're stable configuration that are on 2 phases. So they would change every single phase. And then the last one, the most popular one, is the glider. So this pattern actually flies around the screen, flies around the grid, and will travel as long as it is not stopped by some standing structure. Oh, okay. Sorry, Keynote's acting up. So, that being said, we have also examples of early games that use procedural content generation. So one of the earliest ones called Elite. Now Elite was interesting specifically because it had quite a lot of generated content for the time. So it contained 8 galaxies, each with 256 planets to explore. It's a game that basically created the space trading genre, which is still alive and well today. It's often quoted as a huge inspiration for a game called EVE Online, which some of you might be familiar with. So back then, well, the interesting part here is that a single seed number often is the source for the whole generation of the universe. So we see that pattern again in modern games. We'll get back to it later. It was also fairly interesting on its own because it had a lot of follow-ups, but also because it introduced 3D flight sims as well, like 3D space flight sims to the gaming universe. And those were kind of rare beforehand. So another early game that is interesting for our subject today is the 7 Cities of Gold. So that's also very much a flashback. Now, this game was, I'd say, a spiritual ancestor to Civilization. So you'd play Spanish conquistadors that would, discover the new countries, and here the game packed with a generation engine that could create a totally new continent for you and save it on disk. So here again, that allowed for a lot of content to be packed in a very small floppy. The thing that was interesting back then is that one of the things they tried to achieve, and it's one of the first games that did it, is they really wanted to reduce load times. So they came up with a system that could actually stream off of disk while letting the player keep playing. We're talking Commodore 64s and 8-bit computers then, so I think it was one of the first real examples of this kind of tech that we see constantly nowadays, right? Even though you still see common day games with load times, so that's kind of interesting too. That's about that. For this, one of the last old 8-bit flashbacks I wanted to talk about was something called the Sentinel. This one I found also fairly interesting because it managed to pack 10,000 levels on one of those disks. So that's quite a considerably high number of levels. The whole game concept was based on the idea of, if you can see at the bottom right, the Sentinel sitting atop the highest point on the game board. So basically you would start somewhere at the lower levels and you'd have to accumulate energy to make copies of yourself. You were this robot. Also one of the first real full 3D games of sorts. So they'd place you, you'd have to look around this board, find a spot where you could actually hide from the Sentinel. The whole game was based on, what's going on here? That's quite interesting. Stop breathing so hard, you're sucking the oxygen out of the room. Wow, okay. I'll try to continue. So, right, so this game is all about energy management. And you were trying to basically raise your elevation level and to get to the elevation level of the Sentinel, because the only things you could basically take energy out of on the board were other items that you could see the base of. So anyway, the big feature I wanted to talk about here was really more the 10,000 levels being generated from a single seed. Yeah, so that's about that for here. So now we're going to move on slowly to more modern times. Well, starting with, again, a very old game, Rogue from 1980. I think a lot of people here, like, it's very popular nowadays to talk about roguelike games, and also some concepts that it introduced somewhat, like permadeath and, you know, like games that have a high difficulty levels are really popular nowadays. So, you know, the ancestor is right here. You can see two different iterations of this. The first one at the top is Rogue itself in all its ASCII and ANSI glory. And right underneath is another game inspired by it called NetHack. And again, the reason we're talking about this in this talk is because these games had totally generated dungeons, except for NetHack that had some fixed levels at some points in the game. But most of the content of these games was procedurally generated, so it brought a totally new experience every time you play it. Now, most modern games, like most modern gamers would think, well, this is what inspired two huge big names, which would be Borderlands from Gearbox and Diablo 3 from Blizzard, right? But those are not games I'm going to talk about as far as modern games go. I'm a lot more interested by two other games. The first one of them being Minecraft. Now, Minecraft is pretty much a household name now. Every 3 to 4 year old kind of know what it is. A lot of people my age also appreciate it for different reasons. One of the things that's interesting here is that the whole game world is generated from, again, a single seed, pretty much like the old games we were talking about a minute ago. It features biomes that can vary from jungles to deserts to snowfields. The world itself is actually virtually infinite. The only limit to it is if you go far enough, like division floating point division errors will start screwing up your gameplay and you'll fall through cracks in the world itself. But typically, I think there's even a blog about this, a person that's trying to reach the outer reaches of Minecraft, his own level. And you know, he has to set up a rig on his keyboard where his character is going to walk straight for days on end. I think they're still trying to reach the famed error zones. So we're talking a huge game, like a huge area. And, well, one of the games that inspired Minecraft is even more interesting from a purely procedurally generated content angle. And that game, you might have heard of it, maybe you didn't. It's called Dwarf Fortress by a company called Bay 12 Games. Now, Dwarf Fortress, interestingly enough, is a modern game, but we're going back to good old ASCII art. Now, this game has quite a following, cult following. Now, I took the risk of talking about this today because I figure we're a bit of a subculture ourselves in the demo scene, so I figured it might interest some people. The thing to know here that's kind of interesting in the way they generate their world is that you have one game per world. The player, once starting the game, can determine the map size, the natural savagery of that world, the mineral occurrence, all sorts of factors. And once you're ready to actually generate this world, the WorldGen will start by doing randomized elevation maps, fairly straightforward stuff, temperature mapping of that world. Then it'll go on to do rainfall projection maps from this. Then it will generate drainage values for those territories. So, you know, they're simulating a whole fantasy-like environment planet at this point. Then they'll put vegetation on top of that. They'll estimate salinity of the water, depending on the water level and things like that, too. So that will impact that vegetation. Once that's done, they start calculating things like, is this an evil section of territory or a good section of territory? Is it wild, savage, or benign? Is like the life, the ecology easy on the players? Once that's all calculated, they wear away the mountains and think this is all so far. There's no 3D or anything like that. It's really just a grid-based map at this point. Again, once that's all done, they establish flora, fauna, and sentient populations of, you know, the typical RPG tropes like orcs, goblins, elves, and all these things. Dwarves, obviously. Once the WorldGen ends, the historical ticker begins in this game. So what this means is that they will often simulate thousands of years of gameplay, of automated gameplay, before they actually plunk you down in this world, which results overall in the type of experience where if you establish your dwarven base in some secluded spot and you find an empty cavern, you can often find stuff like you'll explore that cavern. At the very bottom of that cavern, you'll find a skull and a cracked jawbone and some sort of tool in the corner. And then you'll realize that there's the names of all these dead things as ancestry scratched on the walls. So they actually really simulate all of this. And funny enough that you can actually sort of, you know, see this thing in actual gameplay. So I thought that example was fascinating because I don't know of any other game that goes to these lengths to basically establish a backstory. Now, we're going to move on from historical things to talk more about the actual concepts behind procedurally generated content. So the little picture here is because we're going to talk about Ontogenetic and Teleological, or what I prefer to call it, simulation or heuristics. Yes, we're splitting hairs at this point, but that's okay. It's worth looking into what we're talking about. So Ontogenetic is typically taken to mean based on visible or morphological characteristics, and teleological, sorry, is about exhibiting or relating design or purpose, you know, from nature. So basically, if you compare it to simulation, the imitation of an operation in real-world process over time, and you can also talk about, at that point, heuristics, which are rules of thumbs that you would follow to come to a desired result, even though sometimes you might have some problems that come out of that because you're not simulating reality, so to speak. The reason I think this is all splitting hairs is that technically you're doing a computer simulation. You'll never be able to emulate the full complexity of real life, right? So as it comes down to it, that's how I see that. Now, a few of the very base techniques that probably a lot of you are already familiar with, especially if you're in the graphics world, but I'll go over it for the rest of the audience. Perlin and simplex noise, that one is like very well known. So that's the work of Kevin Perlin that we see pictured here. It's a core block for a lot of procedural generation algorithms, for landscapes, textures. You'll often find it for fire, clouds, smoke. You use it to generate textures, things like that. What's interesting about this function is that it has a pseudo-random appearance, yet the details in it, as in the image you see there, are all pretty much the same size. So that makes it a very useful type of noise. If you use multiple copies of it, you can then create a great deal of varied procedural textures. And small fun fact about this, it was apparently developed originally for the movie Tron back in the 80s. The simplex noise one is basically a more efficient implementation of this algorithm that Kevin Perlin came up with himself, actually. So a small note in my talk notes, which you'll find on the GitHub, which I will talk about later, the GitHub project. You'll see all the references to these things if you want to find out more about the details of how these things work. So more ontogenetic tools. So technically, Kevin Perlin noise is fractal in nature. So I'm just mentioning fractals here, and just as a another tool that's a rule of thumb type thing that can allow you to generate things that look like nature. So L systems here are another good example. They're often used to generate vegetation type growths and things like that. Teleological tools, more like simulation type stuff. So cell automatons are quite interesting and can be applied in a ton of different ways. So these two little pictures there are from a Gamma Structure article I found, again, referred in my research notes. So you can see how you can use cell automaton to do things like distribute water levels. And in the context of the games I've talked about earlier, that's actually, you can easily see how a game like Minecraft could simulate water flowing down a hill, or more like Dwarf Fortress, actually. Well, I won't get into the details of water simulation in Minecraft, but the other thing I wanted to quickly touch upon was genetic algorithms. So the picture you see here is from an old game called Core Wars. there's a few projects that try to apply genetic algorithms to this game of Core Wars, where they make random programs. Core Wars was conceptually programs that were trying to overwrite each other's memory, and the game was to write a program that would be most aggressively successful at this. So when you cross that over with genetic algorithms, what you're trying to do is test different approaches with randomness. You cycle with all these algorithms, right? So you create a pool of random algorithms, you pit them one against the other. You evaluate their fitness by how well they succeed in the game. You take those, sometimes you combine them, or sometimes you take them as is, and you create new generations, and you take the best ones, and you rinse and repeat until you get, hopefully, unusually, to something that resembles an appropriately effective program at winning that particular simulation. All right, so I'm coming to the part of the presentation where I'm going to talk a bit about some code. Now, before code, which might be something a lot of you want to see or not, it's always difficult to see which is the more exciting part for people, but I want to touch again on something slightly more theoretical. So the current Android tech landscape. So as you're probably aware, since you're attending this conference, harnessing the power of modern graphic chipsets is a very good place to start when you want to turbocharge performance of things like the simulations were talked about, and if you want to generate your content very rapidly in real time. It's a concern because even the game I've been talking about, Dwarf Fortress, has a typical startup time of 20 minutes when it generates that world. We're talking about like a fairly, you'd think, simple game, right? So procedural generated content, if you push it far enough, is actually quite computationally intensive. Right, so the techs that are available on Android and mobile in general are, the first one is OpenGL ES 2, 3, and 3.1. Obviously there's OpenGL ES 1, but that's not very useful for our purposes. Right now, 2.0 is basically, I think, the standard on most mobile devices. We're starting to see devices with 3.0 and 3.1, which will start supporting natively, will start supporting natively programmatic and compute type functionality has only been announced, like I think last week or 2 weeks ago. So before we see devices in the wild, it's probably presumably going to be some time. Otherwise, on Android, you get something called RenderScript, which is, I think, the platform's equivalent of OpenCL, the Open Compute language. So the thing with that is, obviously, it's limited to the Android platform. The fun part about this technology, though, is that it technically is available on very old devices. You can go all the way back to Gingerbread. And if you write a program that uses RenderScript technology, you will actually be fairly compatible with all these other older phones. It doesn't mean that you'll get a whole lot of mileage out of it, but you don't have to write your code twice. And the latest and greatest, we have the Tegra 4 from this year and the K1 coming up. Now, I put this slide here because the K1 is kind of interesting because they've announced that as a mobile platform, it's actually going to support CUDA natively, and it's going to support desktop OpenGL. Now, if you're me, and what we're trying to do here is to develop a small framework to help people actually prototype shaders and prototype compute type shaders, the K1 is very intriguing as far as performance goes, but as far as compatibility goes, there's a bit of a question still, right? So if you don't want to develop twice your code, what do? Do you actually go with that or not? So since here we're trying to talk about a framework more, the conclusions of all of this is that the approach I'm going to propose is more going to focus on OpenGL ES shading language, because that's actually cross-platform compatible with iOS as well as Android, right? So, and presumably other mobile platforms. So you're going to get a lot more mileage out of an approach like that. And later on, I might explore RenderScript options, but that's not for now. So I've been talking about this GitHub project, right? So if you have smartphones at this point, you might want to take a small picture of this. It's very early days still. That's the QR code to actually get to the GitHub page. So the motivations behind this is that, as mentioned, I'm part of the Android Montreal GDG. And one of the big things we try to do is introduce new people to the platform. There's actually quite a shortage in Montreal of Android developers. And also we're trying to always bolster our membership. So a nice way of doing this is to give beginners courses, right? Which we're fairly good at right now. But the thing is, once you've done the beginner stuff, usually people want to learn the beginner stuff to get somewhere more interesting. Like, it's not everybody that wants to make a simple app. A lot of people want to see more graphic stuff, right? They want something a bit cooler. So the whole goal here is to provide them with a very small, something like if you've ever seen this website Shader Toy, one of you here, maybe here or maybe at the other keynote, but one of the people, one of the speakers at NVScene is actually the creator of this site, awesome site. It's a repository of fragment shaders, and they run live in the browser. And the great thing about that is that you can actually edit the code, right, and see live what your changes are bringing. Or you can take your own code and start prototyping it very quickly. So Android is a slightly different platform, right, than the web. So you have different support of shaders. There's a few projects that do this on the store if you look for them. But I was looking to add something to this. So the point that's going to be more interesting with this project is going to be the addition of a small compute segment. So hopefully the fully realized vision will be a platform they can use, fairly simple to use, well commented, and that people can upload their little shaders to. It will be backed by a website, and people can do fast prototyping, share with friends, and hopefully make cool stuff. Right. So before we actually dig into the code examples, I want to talk about modern Android toolchain. So that might actually be a bit controversial, but I'm going to go for it anyway. The typical tools for Android have been Eclipse, running an Ant build stack. A lot of people have had good success running Maven. Now, last year, they've announced at Google I/O that well, I shouldn't say the platform of choice, but the new build tool of choice would be something called Gradle. The interesting thing that brings to the table as far as Android is concerned is that you have a few, for those of you that do Android, this is not news, but on Android, the old build tools made it kind of hard to actually make libraries. As we'll see in the example code, Android packages usually have resources attached to them. And if you ever wanted to do a library with actual resources in it, up until the time that Gradle came in, it was actually impossible. The only thing you could distribute was a jar, a library jar. So they've added that kind of capability. They've also added flavors that they call. So flavors allow you to have very different builds of your application, something that was also difficult. So all around the table, without getting into too much detail, Gradle brings a lot of flexibility to your builds, and you can make a lot of different versions of your app, which is quite interesting when you have a pool of potential devices that goes above 3,000. So just for a typical release for our app where I work, we hit about 3,200 different types of devices, and we don't even support devices before ice cream sandwich, like in version. So we actually eliminate a lot of the potential users that way, and we still have to support a ton of devices. So different flavors are actually very interesting at that point. The other tool that we'll see is IntelliJ IDE. It's an alternative to Eclipse, so I personally like it, and I just wanted to touch on it to say that it's worth making an attempt. I was an old Eclipse user, and I have seen the light, so I wanted to share. The last tool, which I will be showing you, which if you don't know about, I think will be a very good takeaway from this talk, is something called Genymotion. I've learned of this actually last year when I got in contact with GDG people from France, GDG Android from Paris, I believe. And these guys are behind this project with their actual corporation they work for. The corporation does embedded software, so they do Android onboard for cars and things like that. And they came up with a blazingly fast, I want to call it an emulator, but it's more of a simulator, a bit like what you get on iOS. So I'll be showing you some shader code example running off of my machine, projected a bit later on, with this tool. So I really encourage you to look it up. If you're an Android developer, it will change your life, very simply put. And I quite believe that. All right, so framework architecture. So don't be scared, this is not an actual diagram. I've tried to keep it extremely simple. And looking at the time I have to talk to you about it, that was a good idea. So we'll start right away with something called GL Surface View. Now, the thing I recommend to people, a lot of the approaches I've seen in the demo scene, specifically when I hear about coding on Android, people will say, well, forget about Java, just do it, do native code. That's much better, right? Like that's what people are used to, especially from the graphics background. And I'm here to tell you, yes, that's true. It's quite compelling to actually do C++ on the Android devices, but you do lose a lot. And here I'm going to just propose an alternative. So GL Surface View is the first thing that you will encounter in my example code. So I will now take a brief break from the slides. I will jump into the code. I will try to go as fast as possible so I don't explode my time limit. Sorry. Yeah, this is the part where it's going to get difficult. Okay. So this is the shader surface. So like in Android you have views. So this is a typical view. I'll try to fly by because I see that time has gone quite fast, but you can get all this code off of the GitHub as soon as this presentation is finished and I push to GitHub. So things to note. So the shader surface is actually what you put, it's the view widget that you will be putting in your Android view. So for those of you familiar with, yeah, this is really the point where the microphone starts. It was a good idea at first, but now I'm kind of worried about it. Okay, no, we're good, we're good. All right, so very quickly. All right. All right, so your typical Android view, your main view would be defined as such. It's an XML file where you define your top wrapper and where you define your actual content. Now, you just would put whatever the class of your GL view is in here with a few parameters, and that's it. You've just defined the full screen view for your application. What's interesting about this is that once you start going through less native approaches and more with the platform, it'll give you a lot for your money. Like Android developers here probably are very aware of the slide I'm going to show next, which is the wonderful Android, wait, there we go, the Lifecycle. Lifecycle is somewhat annoying to deal with if you're usually just native, because whenever the device falls asleep or you get a call or you're interrupted for some reason, you have to deal with all of this. And a lot of the native code I've seen doesn't deal with that very well, because you have to start thinking about interruptions and things like that. So again, to go back to the actual surface, you'll see that the code that handles this is actually quite simple. All right, so you just have your constructor here. Here, short example, you can actually get values from the XML, so you can define your own attributes and decide to configure things that way. That can be very useful. The initialization of a view is here, fairly simple stuff, but I'll go with it quickly for people who might not be as familiar with OpenGL. So you set the version that interests you. In this case, it would be ES2. Then you can set your debug flags, which is fun, and then you don't have to constantly call on the OpenGL stack to find out if an error happened on the last call. So this will pop a Java exception for you whenever there's a problem with a bit more descriptive text. And here you see, well, basically that was my parameter I got from the XML. So I decide what type of shader I will be using. So all the shaders I'm going to be showing in the live examples are things I actually took from different websites out there. They're not my own creations, so just to make that clear. And then the last step for that surface is to set a renderer. And we'll go into the details of what exactly a renderer is, but that's where the actual OpenGL code is ultimately being called, and that the draw function will be called at every iteration. And here there's You also have the possibility of defining a GL view surface that will not be updated continuously. So when you're in continuous mode, what's interesting is that you have a separate thread. So if you're aware of the Android and pretty much the iOS model, on mobile and on a lot of other platforms, but you're going to have one big render thread that's going to be rendering your view and handling some of your on-click events and all these type of things. And if you start making anything computationally intensive in one of those processors, you're going to end up with jagginess and all the the problems that are associated with that. So what's fun here is you already have a thread specifically dedicated to your WebGL view. You could have many views on the same screen, so each would have their thread. So that's already a fun model when you're using the continuous option here. If you're not, it's only going to refresh whenever you say it's time to refresh and it's dirty. So that can be also interesting for cases where you'd have, I don't know, a model and then you'd use touch events to rotate that model and look at it when it's less of a demo type situation or a game type situation. Some of the code here, if you're interested, you can look at the example, shows how to handle events and how to dispatch events to the other thread. That's the code right here. It's a simple call, as you see. You call something called queueEvent. You pass it a runnable, a Java runnable, and it will execute this on the rendering thread, separate from the UI thread. So if you've ever lived with the pain of having to handle all of this on your own, well, it's not a huge pain, but it makes things simpler, and we always like that. So, very quickly going back to the slides. Right. So the other two concepts, the big concepts of the code examples, are simple shader gadgets. So as I mentioned, there's a site called Shader Toys that's already taken up. So we'll call them gadgets here, which is, if you're from anywhere from France, this will bring back old memories. So simple shader widgets. I'll show you first the result on Android, what this looks like once implemented. Right, so again, just a quick note, this is Genymotion in action. This is the simulator I was talking about. So this is a simple Plasma, well, Plasma, it's not technically Plasma, but anyway, it's a shader code that I took from a nice browser directory site. So as you can see, it runs fairly smoothly, obviously, since it's actually using the GPU on my Mac. I'm happy to report this works absolutely gorgeously on the Tegra 4. Not so nicely on the Nexus 5 for some reason. It actually slows down to about 2 or 3 frames per second. If ever you want to tweak these things and you're interested, I encourage you to go and check out our Git project later on. So what's behind this example code? Right. So I'll go through the rendering example and then I'll call things to a close. Right, so shader gadget renderer here. Actually, you know what? I'll dupe the screen because I'm tired of craning my neck like this all over the place. Give me 1 second. Sorry for the delay. Right. There we go. Okay, that readable? Yeah, okay, good. So, shader gadget renderer. This class is called upon from the surface view. What's interesting there is you can just switch renderers around, right? So that's quite nicely modular design. This shader gadget renderer will load your fragment shader or your vertex shader if you want to experiment with it. Currently, it's loading it off of the assets directory, so it's like literally a file that's in there that's being accessed. I have code that I will be pushing very soon that will actually get this from the backend I've been talking about. Now, handling of this is actually fairly simple, and small feature of IntelliJ I'd like to show is that you can, you know, as a lot of modern IDEs, you have a lot of plugins that allow you to do fun stuff. Like, for example, if we want to look at that plasma from earlier, you know, you get syntax highlighting for your code right here. So that's interesting because it makes it a lot easier to debug and, you know, find out what's going on. A lot of shader example code, if you've ever looked at it, is, you know, it just injects these things in a big string in the header. So that's not always very pleasant to read or easy to understand. So that's one small feature that will help if you're starting out with this stuff. And if I go back to the renderer, there we go. So the renderer itself is called, the action is basically happening here on draw frame. Things you might want to note is that the setup is done through two calls, one on surface created, where you would typically set up your textures and things like that if you have some to set up. This is also called when an Android device wakes up from sleep. So comparatively with what I was talking about earlier for the lifecycle, it helps you handle the lifecycle in a very easy and natural manner, which is not something that's always obvious with Android. Here you're going to get a call to basically tell you what the resolution of that surface is, so you can set your projection accordingly. Here's a small example code that actually loads the shader off of disk. Very clean and simple stuff. And am I on time? Yeah, I'm gonna end on that note. So here you have the call to on draw frame. So as you can see, it's like, I think we have a very nice and easy experimentation platform here for a lot of people that are actually a bit like me, starting out or hobbyists. Now, I know my Android stuff, but not everybody has time to look into OpenGL unless it's actually their job, right? But a lot of people like to fiddle with it. So I'm hoping that this project will help achieve that. Right, so small last note. The actual drawing code is here. So this one will render your two triangles on screen, which you know, would fill up the entire screen, very much like if you ever looked at it, Shader Toys operates. And your fragment shader will be called for every instance of the pixel in that screen, and you just put your calculations in there, and you'll get your result. I'll run one quick last demo without going through the code, just to show that if you were going to look up this project, I've actually come up with, again, based on very nice examples out there. This is a game of life. So interesting part about this is it's not very graphically impressive, I know, but the simulation is running on the GPU, right? So that's what's interesting here. So basically you can write shaders that will process, you know, you can add whatever rules you want. If you look up the game of life, there's a lot of very interesting variations that you can try out. You can simulate fire propagation with this kind of stuff. You can simulate, like I explained earlier, water being dispersed around the level. You could do a lot of what I've talked about with Dwarf Fortress with this kind of setup. So the hope is for the project to have something where you can create these shaders, string them up one after the other, send the input of one into the other, and, you know, very basic stuff, but as far as like a proper professional would be concerned, but for somebody, a hobbyist, I think that it's fairly compelling. So that's about it for the technical part. I'll just move on with closing at 1:45 on the dot. Try to keep things on schedule. So I would like to thank you all for attending this talk. I'm honored that you picked me instead of other alternatives. I hope it was worth your while. Now, the GitHub project is, again, here on the QR code if you want. If you want to contact me, any questions or suggestions, or hopefully not hate mail, but, you know, if ever you feel the urge, feel free. It's in Caron@gmail.com, and that's my Google page, Google Plus page right there. And I can also be seen sporadically on Twitter under the @Canawish call sign. All right. So thank you. If you have any questions at this point. Yeah, thank you.